Kelso, who will be giving Neuromarkers for Social Coordination, a Dynamical Approach.
Slight change in title, but
Okay.
the same gist. Yeah. So Vittorio has been telling you about the mirror neuron mechanism. I would like to thank Sherry for inviting us, and I'm very sorry for imposing upon you if that's what it is. But I think that she's very courageous to bring people in neuroscience into this picture. It's not neuroeconomics that you're hearing about this morning.
It's the actual science, yeah, that's what we want to know.
So I would say one point is that I'll be talking about interactions in real time between people. And what you heard was what is going on in the head of a monkey or a person when they are confronted with other situations. That's the first part. That's Victoria's part. So this comes from the city of Derry, and it's called Hands Across the Divide, and it expresses the hope for global harmony in societies that have had a great deal of difficulty tolerating each other. So you see a coordination there between two people of very different backgrounds and cultures and religions and so on, and you see that there's a kind of touch between them. Right? So keep that in mind, and we will move from there. Now, with respect to our chairperson, this picture you'll see is in 1982. And one of the things that I'm going to be talking about is dynamics. You saw where things were in Vittorio's talk. I'm going to be talking more about dynamics. And this meeting, this guy up here, you can see in the top right with his arms around Ralph Abraham, a very famous mathematician, and another friend of mine called Michael Turvey. But there's the young Don Farmer. Right? You see him? This guy up here. Can you see Don Farmer?
I'll tell stories on you later.
1982 now. People were thinking about non-linearities and brain function. Here we are in economics thinking about what would be the new breed of economists. It's very difficult to just hold oneself in there getting to this, because shortly after this, the NIH approached me about could we bring these ideas into neuroscience, just as Sherry and many of you are thinking about how can we bring new ideas into macroeconomics. So it was the same kind of thing. We had to configure an appropriate curriculum, and what would the new breed of neuroscientists look like, and so on and so forth. I'd love to talk more about that at some point. Now, 30-odd years later, we have Paul Allen and Francis Collins, who will be known to all of you, saying, today we know that neurons fire and we know they are connected. We don't know how they act in concert to govern behavior. So acting in concert means some kind of coordination, and that's the essential question now. It's not so much where things are, we need to know that of course, but also how they are coordinated, how they act in concert. And actually for me, the name of the game here, you've heard the word used multiple times at this meeting, of coordination. That's the name of the game here in biological systems. And I'm inspired by Howard Petit, physical basis of biological coordination. I do not see any way to avoid the problem of coordination and still understand the physical basis of life. So the theory that we've been trying to develop is called coordination dynamics. I won't go through all this, but it is multi-level, multidisciplinary. Coordination is everywhere. At all levels, and we have to accept it. It's often functional, it's not just structural, and so on. Now, one of the main results that we've found, and this is a summary of it. So just look at this. On the bottom you see segregation and integration. This is the way people think. They think of the either or. Is the brain segregated, where all the neural groups function independently, or is it integrated? And that's the usual way we're doing science here. Actually, I think it's the wrong way. And now that we're a bit more sophisticated. It turns out that some neural groups are working together and some are working independently. And even better, they work independently and together at the same time. Yeah? So it's not an either-or proposition at all. And that's the bottom line. Keep that one in mind when people are saying, is it this way or that way? We heard this yesterday. Is it DSGE or is it multi-agent? Actually, think about the power of both, the both and logic. Or maybe it's neither nor. That would be all right, but it doesn't have to be either or. Can we just get away from the either or a little bit? Just step away from the either or. Right. So one of the main themes here is, bottom up versus top down. One of the chief ideas that came up with Mark Buchanan yesterday evening, this idea of reciprocal causality. It turns out in these kinds of complex systems that the bottom, the dynamics of the bottom is creating modes of behavior at a collective level, and those modes are actually acting down on the way the components are interacting. And this isn't a micro-macro thing, this is a cross-level picture. So you, or typically a scientist, we choose the level of description, and then we try to understand it, right? So what does it mean to understand here? And this would be a picture of how we can reconcile this top-down versus bottom-up notion. And that actually there's real evidence to show that that works. Now, dynamics. In Vittorio's talk, you saw where these neurons, often just a small number of neurons, right? Where they are. And they have firing patterns. So let's talk about the spatio-temporal patterns that are produced when people interact with each other. We're going to get there. Brain rhythms. And this is the secret language of the mind. The brain is a geography of improvised rhythms. So let's just take that as an image. And you can see that these images are associated with perception, attention, the kinds of categories that we make. They come in different flavors. Gamma has high frequency, 30 to 200 hertz. It's in many brain structures. Theta would be associated with memory, and so on. So this is kind of bringing in the idea of not the business cycle, but the brain cycle. These are brain cycles. And it's a spectrum at multiple scales. And we've given them Greek letters, by and large. So this is your brain, my brain, everybody's brain. Right? So you have some very slow, you have some delta, which is associated often with sleep, theta with memory, alpha with attention, beta sometimes with motor control, and so on, gamma with cognition, and that you've got a smorgasbord of rhythms. And each site has multiple frequencies. Yeah? And each frequency has multiple spatial patterns. See this in the bottom. Now, here's the research I'm going to tell you. I'm going to tell you about basically two kinds of research. And I'll try to make it as quick as possible. I'm going to tell you about, first of all, experiments between two people where they are interacting in very simple ways. Yeah, it has to be that. I mean, the question is, always in these complex systems, what is your window into trying to handle the complexity? How do you get into it? Then I'm going to tell you about some experiments where we have a theory, a theoretical model. We put the theoretical model into a computer, and we have the computer drive an avatar, right? And now we have the human interact with a model of themselves. So this is your self-reflexivity property. And I'll not talk too much about modeling. So let's, Sherry was very anxious for me to show you about these early studies, and these are neuromarkers. And there are two people interacting with each other, very simple. Each person is moving their finger up and down. They do that for 20 seconds. Then a shield, actually it's an LCD screen, opens up so that they can see each other. They're just told move your finger up and down. That's the only instruction. And then they see the light, they see the other here in the middle part, and then they don't see them again. So very simple, 60 seconds. Every trial is 60 seconds like that. Purely spontaneous. So this is the spontaneous part. And there's the setup. Two people, we've got 64 electrodes in each person, and that's the paradigm. Everybody got the paradigm? You do your own independent thing throughout, but in the middle you see the other person's hand. Right? That's all. Then the lights go off again and you're back to yourself. Now, let's just show you the kind of data you get here. Here's the finger movement up and down. That's a finger movement. That's behavior. Oops. Here's the, that's on the top. Sorry, this is dual. Then the red and the blue guy, you can see, are actually moving at slightly different frequencies. So in the middle panel here are the instantaneous periods of the movements. And the bottom, which is why we call it social neglect, the bottom is the relative phase between the two. The phase relation between the two, which captures the coordination. If I'm going to dance with you, we are phase related. We're in time with each other in some way, right? So understand that when you see this, this is the relative phase on the bottom, and it wraps. That's obvious because the two people are going at different frequencies. See it? Yeah? Everybody see that? Okay. Now you get a whole bunch of patterns when people see each other. So here's the 60 seconds again. Social neglect one is up on the top left. You also get fully synchronized antiphase. So people are on the bottom left there. They're not really coordinated. Then when the window opens, they see each other and they coordinate spontaneously in phase with each other. And then there's another situation where it's almost initial condition dependent. If you look closely on the bottom right, they coordinate antiphase with each other. This is Sherry's anti-coordination phase. And notice after the lights have gone off again on the right part, there's almost a remnant of the interaction. No longer any coupling, no longer any way for the people to couple. There's no visual information exchange anymore. But you see there's a kind of a little persistence of the interaction. I like that very much. It's a kind of idea of social memory that after you and I go off and do our own thing after this interaction, hopefully there'll be some remnant of it. This is very, hopefully, but I know we're all tired. Okay, so what's the punchline here? You see these characteristic rhythms, and as you can see here, this is quite hard because you kind of want to do this. You see that before visual contact, you just have these mu and alpha rhythms. And you can see FZ and CP4, these are places where the recordings are taken. Key thing here is that when they have visual contact with each other, when there's visual information exchange, you see a new rhythm called the phi rhythm. And it's in a particular place, CP4, centroparietal regions of the right hemisphere, which happens to quite nicely jive with where this mirror neuron system is. Yeah? Yeah? So if you look at that, again, let's not get too bogged down in this. These brown regions are this phi rhythm when people interact with each other and when they don't. Okay? So that's a new rhythm. It's a purely spontaneous situation. Now you can ask another question. What would happen if humans intentionally coordinated with each other? Right? So here we go again. I'll leave that out right now, but it's the dynamics here are very sensitive. When you're coordinating, as you see, the relative phase is a nice coordination measure. You see this phi rhythm, and even when you just go slightly out of rhythm, it drops out, you see. So you've got, it's a very sensitive, dynamic measure of social interaction. Remember, it's two people. This is not just me watching the other, it's two people's brains. And this is a model which actually I won't go into in any detail. It's really a redescription of the thing. It tells you about how these rhythms interplay. The key thing here is that on the left, there is no activation in the mirror neuron system, and on the right, this is especially for Vittorio, on the right, you see that there's two aspects to this phi 1, which comes up when you're just doing your own thing, and phi 2, which comes up when you are coordinating with the other in phase, right? So there you see the interplay of these different rhythms in the brain in this kind of a context. Now, there's not only neuromarkers here, there's neuromarker dynamics. I don't have time to go into this. If anybody wants to see this, there's a new paper called The Metastable Brain, which has just come out in Cell. And if people want to read about it, they can. So it's not just the neuromarkers themselves that seem to distinguish these states of affairs, they themselves have a dynamics or coordination, and that needs to be looked at. It's not a sort of rigid coordination. It's very much an escape dwell. The two rhythms come in, go out, come in, go out. It's metastable. Yeah. And you can see that nicely here. This is typical of a brain doing multiple different things. On the left, you see the range of rhythms. The frequency is on the x-axis. You see these at different locations. But the key thing that you see here is that some groups stay together. The phase, the ones that are connected, they stay together. And some groups just do their own thing. So you've got both of those things going on together. Yeah. You see on the dynamic part, 3 different ensembles are just connected. They're just related to each other, and the others are doing their own thing. So this is this notion that you have both processes going on, not just a cooperation, but a kind of cooperation competition process. And a nice model of this, it's called a chimera, for obvious reasons. On the bottom is actually an array of oscillators. Neurons oscillate, it's very clear. And what you see is that under a certain kind of non-local coupling, some of the oscillators couple. Those are the ones that are going together, and others are going independently. So there's a coexistence here of both a coupling, a coordination, and an independence in the chimera. Yeah? So that's quite amazing for me. Right? So let's think about that. And of course one can go on and do this with source localization and source dynamics. The great Sherrington was an inspiration of this. And in the bottom you see the activity index, and you can trace the sources here and the source dynamics. And that's, again, another story. But it can be done. Everything I've told you about is just the spontaneous coordination that occurs between people with visual information exchange, visual coupling. The intentional case is a different case. So here's pretty much a similar paradigm, except before vision, they are told, okay, do your own thing and continue to do your own thing when you see the other, relative to do your own thing, but when you see the other, go in phase with them, versus when you see the other, this is the anti-phase condition, do your own thing, but go anti-phase with them. That is, go in the opposite direction to them. So these are newer experiments. Again, without going into all the details, this intrinsic case is the first case where you're supposed to keep your own rhythm. The second is the in-phase, the second box, and the third is the anti-phase. And a measure called event-related desynchronization, this is a measure of these rhythms. You can actually see that the anti-phase showing the greatest amount of event-related desynchronization relative to the other two conditions. And again, there is this kind of cascade across the different brain regions. But I think everybody can see the green and the blue here are just two different hemispheres, the electrodes in two different hemispheres. And what happens is that there's greater and greater engagement in the anti-phase condition in this 10 to 12 hertz range, in this rhythm, that is the 5 rhythm range. Now, let's ask, this is very interesting, I think. You'll get it in a minute. One of the things we know is that when you go anti-phase, it's harder to stay stable than when you go in phase. 5 minutes, excellent. And that just is shown here on the left. That's the behavior. And we have modeled this for eons. It's a well-known situation that if you start out anti-phase and increase the frequency, drive it, kind of like Mark's experiment last night with Harry Swinney, activate the system, it switches spontaneously from anti-phase to in-phase. It's well known about that. And here is the phi under these experimental conditions, with and without, during the anti-phase, the anti-coordination case itself. And notice here, it's quite interesting, that on the left, during anti-phase, there's no phi at all. there is during the intrinsic part of the experiment and during in phase. This is not intentional in phase, but no phi. On the right, there is obviously a phi when you're doing antiphase. And you ask the question, why is there no phi in antiphase in this situation? Let me go back. It's easier this way. And there is a phi in the other case. Actually, the reason is it's related to how well they can anti-coordinate. Yeah, and that's very simple. If you can anti-coordinate or anti-phase very well, you get your phi sitting there, large as life. But if you can't, you don't. So you have to see brain and behavior at the same time. Right. Now, I won't go into this, I only have a couple of minutes, but one can now ask about information exchange between your dyads, and you can calculate information theoretic measures. You can now see what the brain dynamics look in this experiment where you ignore versus not. And what you see is the typical pattern in the antiphase condition engages more frontal regions. You have this parietal occipital region as well. So one can do this not only just within brains, but also between brains. I want to get to this very quickly, because I think it might be a kind of different paradigm. So what's done here is that we put these equations that we know very well, that have been empirically verified for many years, 20, 30 years nearly, and we put them into the computer. We drive a hand. We basically simulate the experiments, but now with a virtual agent. Yeah, and this allows us to really play with the parameters of this system. You know, what the parameter space of the system. Okay, well, what happens then is that you can make the avatar go contrary to the person. Yeah? So you can program the avatar saying, the avatar wants to go antiphase, but you're told to go in phase. And what happens, I won't go into all the details here, but there are emergent strategies. These papers have been published, and there's going to be a lot more of this. There's a very nice, so what you're seeing here is the time series of the finger movement of the avatar and the time series of the finger movement of the human. And what happens is you get entirely new strategies created. A key thing that happens is that the subject, under these conditions, perceives that the other, which is a machine that contains the equations of motion that are characterizing the coordination of the person themselves, the human thinks that they're messing with them. Actually, they use 4-letter words. Another 4-letter word. So there's some point where the human wants to go in phase with the avatar. The avatar, because we've been clever, has been programmed to go anti-phase, and the human says, So that's deceit, yeah? That's deceitful. And it's kind of like a non-verbal Turing test. And you can really play this game. It's a lot of fun. A lot of fun. So one can explore that. I can't go into all the details. But it turns out that this attribution of agency has to do with the coupling strength between you and the other. Finitum, right. So one can do that also with the brain. It's very interesting tutorial. This is new work with, you maybe know, Guillaume Dumas. And one can get the self-other network, and again, in the same paradigm, but now just between you and a virtual agent. So this allows the whole thing to be. I want to, yeah, so, right, let me just leave you with this one. Just to get the last point here. We talk about agency. We talk about agent-based models. What about the origins of agency? What in human living things? What is the origin of agency about? This is an old experiment with a baby, right? The baby, as you can see on its back, it's only 3 months old. And babies spontaneously kick. They have spontaneous organization. Yeah? That's a very nice thing to have for a living thing. It moves. Yeah? Now, if you tie a ribbon to its toe, and the toe is connected to a mobile, probably in English we'd say a mobile, or would you say mobile? And I've got Americanized, haven't I? Well, the baby suddenly realized, you know, this is me kicking, not I'm changing the world here. This is the origins of agency, right? And this is an old experiment, and it was measured just response rate. But you can see that the coupling between what the baby is doing and its effects on the world, the mobile moving, and the world's effect on it creates the notion that, hey, this is me. I am doing that, not some mechanical agent. Right? And it's because it's a collective state, a collective pattern. It's not just the agent, it's not just the agent picking, and it's not what the Herb Simon, the world is complicated and the human is simple. Yeah, come on. Yeah? So there's coupling at all scales, bidirectional, that's a key aspect. It's no longer I think, therefore I am, you know, cogito, ergo sum. It's I link, therefore I am. Think about it. Thank you very much.